Tonight's speaker is David Martín from the Department of Environmental Protection. Good afternoon. I'm David Martín. I'm going to talk to you. I want to talk to you about the functional annotation of chemoreceptors. It's my thesis theme. Well, I'm in the Department of Environmental Protection in a white building. I'm working in the laboratory of Chemoreceptors. And my thesis is focused on the chemosensory pathways and chemoreceptors. The chemoreceptors are the first actors in all these two component system with a periplasmic ligand binding protein which has the functional sense, this is the signal, and transduce it across the membrane into the signal domain. And this domain will activate some kinases and some response regulator that feeds into different functions that chemotaxis, bioinformation, hormone sensing, virulence, and other functions. So now the signals that triggers all these processes is very important for the knowledge of these processes, and understanding of this is the main theme of my thesis. Well, we do an approach, an in vitro approach, studying this Ligand domain to know the signal, and then we do a screening to know the signal, and then we go for phenotype changes and characterize all the protein of the chemoreceptor. Well, to illustrate all that, I'm going to talk to you about one of our recent work published. That is the identification and functional annotation of this protein, the PA5072. First of all, we did some bioinformatics, and we saw that this protein has a Ligand binding domain that is a homolog of a known, of a previously known Ligand binding domain of MCPS from Pseudomonas putida. This is the first member of the new family of chemoreceptors characterized to bind organic acids in a bimodular way. And as we see, there's many residues that are conserved. Importantly, these R's here, and these Y that are important for the recognition of these ligands. The secondary structure is also conserved with two short helices, then a large one, two short helices, and a final large one. And when we did a 3D homology modeling, we saw that this in fact is helical bimodular, like is the MCPS. So at this point, the question was, does this Ligand binding domain sense organic acids, as in the case of MCPS? So we produced a recombinant domain and started a ligand screening using a thermal shift assay that is based in the idea that the binding of the ligand to a protein stabilizes the structure, and this increases the TM of the protein. So using thermal shift assay with a high throughput cleaning using 96 well plate, we encountered that there are some hits that reach or go further a threshold of an increase of the TM of 2 degrees, with a maximum for the compound alpha-ketoglutamate acid, with 5.2 degrees of increase. So to verify all these hits, we use another method, the isothermal titration calorimetry, that let us know how is the binding and know the thermodynamic parameters and the constants of the binding. We test all these hits for thermal shift assay, and we test other compounds like TCL cycle intermediates and other organic acids and related compounds, but only alpha-ketoglutarate bound to this ligand binding domain. And so we term this protein like MCPK, that is methyl accepting chemotaxis protein for alpha-ketoglutarate. An interesting thing is that in the binding we encounter two events. A first event of binding with an affinity of 300 micromolar, and a second event with an affinity of 80 micromolar. This means that there's a positive cooperativity in the interaction with this ligand, in which the first event increased the affinity of the second event. This is interesting because until now there was some chemoreceptors that present negative, present in cooperativity, but only in a negative way. This is the first chemoreceptor that present this positive cooperativity. So we wanted to know more about the interaction between this ligand and the protein. So we performed analytical substitution assay to know more about the oligomeric state of the ligand binding domain. In the sedimentation studies, without ligand, we can see two species here and here that correspond, this one to the monomer and this one to a species that represents a fast equilibrium between the monomer and dimer, but we cannot see the dimer. It's only in the presence of 1 millimolar of alpha-ketoglutarate when we lose these two species and we can see this one species that corresponds to the dimer. So the presence of alpha-ketoglutarate bound to this ligand binding domain stabilizes the dimer. To know about how this dimerization happened, we performed equilibrium studies using different concentration and in the absence and the presence of alpha-ketoglutarate. So in the absence of alpha-ketoglutarate, the dissociation constant of the ligand binding domain dimer is about 55 micromolar. But in saturating concentration of alpha-ketoglutarate, this dissociation constant goes down to almost tenfold. And this means that not only the alpha-ketoglutarate not only stabilizes the dimer, but the binding to one monomer enhances the binding to the other monomer. So promotes the dimerization of the protein. And this is important because the HBM family acts always in dimer form. So, but now, what's the function? We perform some quantitative capillary chemotaxis assays to see if the function is chemotaxic, and we wanted to quantify this response in a dose response manner. In the wild type in black showed the highest response at 500 micromolar concentration of alpha-ketoglutarate that correspond with the ITC experiment in where the first event has an affinity of 300 micromolar. So at this concentration, the protein is saturated. If we do deletion mutant, we can see that almost all response is lost, but with a little of response that may be due to energy taxes. So it's only when we combine this mutant strain with a plasmid harboring in the gene, and we restore the phenotype in the same way that we did in the wild type. So MCPK is the primary chemoreceptor for alpha-ketoglutarate and mediates the chemotaxis toward this compound in Pseudomonas aeruginosa. Well, we did other experiments to characterize all the process as like gene expression to see if this compound modulates or not this expression of the gene, and if this chemotaxis response is involved in the colonization of plant tissues, but because of a matter of time, I don't want to talk you here about that. Just to finish, what these in vitro approaches with recombinantly produced sensor domains make us identify and functionally annotate the MCPK gene from Pseudomonas aeruginosa, this protein as a chemoreceptor, and that this approach can be used also to annotate other sensor proteins like sensor kinases or proteins that have sensor domains to know the signal, the trigger of the processes and how all this functions. So thank you very much for your attention. Do you have any questions?
Thank you, David, for your interesting presentation. Perhaps some people in the audience are not familiar with calorimetry. Could you please explain us very shortly which kind of tests could you carry out with calorimetry? Because it's important technique you are doing.
Well, in this case, our calorimetry method is the isothermal titration calorimetry. That is a method that measures the changes of the heat changes in the solution and can measure if the reaction between two molecules is exothermic, endothermic, and we can calculate the enthalpy and the affinity and all the thermodynamic parameters using a cell with a reference cells, a reference cell and a cell with the protein of interest in where we inject the compound that we want to test. It's more
Thank you.